Hi, everybody. We're going to talk about the Euclidean algorithm, which is basically we're getting into Module 4 now. And in the first section, we talk about the Euclidean algorithm. And the book has a really nice visual, so I'm going to talk through that a little bit and then tie it off with the next section as well. So this is kind of, we've been doing a lot of work with linear combinations and prime numbers and composites and all that, but Euclidean algorithm is really starting to get into the guts of what number theory, or what we do in number theory. And so we're going to take a look and kind of walk through a visual explanation of what the algorithm is doing. Excuse the red lines at the top and bottom of the screen. I'm not sure what's going on with my equipment here, but for some reason it wants to put the lines in there. You can ignore those. I probably will. Anyway, so Euclidean algorithm. So let's say that we want to find the greatest, or we want to divide up the numbers. Let's use 150 and 66. Okay. And what we're looking for is, what's the common divisor for these two? That's kind of the next section, but the Euclidean algorithm will help us get there. So the first step of it really is we're going to be slicing this rectangle up. And what we're essentially going to be doing is we're going to be slicing it up until we get a square, until it's all squares. That's the goal. If we can get down to a square, essentially that square then is the thing that could fill the rest of the rectangle and be our greatest common divisor. So the first step is we're going to look at this and we're going to say, okay, how many times can 66 go into 150? So what we'll do is we'll kind of draw, so you're going to have to forgive me a little bit that these are supposed to be squares. So essentially this is 66, this is 66. And that means we have 18 left over on the end here. So one way we could write that is we could write that 150 equals 2 times 66 plus 18. Essentially, we're looking at, it's division. It's what we would do if we had, say, the improper fraction 150 over 66. We would rewrite that as 2 plus 1866, where 66 goes in twice, and we have 18 as a remainder. So we essentially have these two things that are squares right now, and we have this long rectangle that is now 18 by 66. And we're going to repeat the process. So I'm going to go through, I'm going to say, okay, how many squares can I pull off 18 by 18? So all of these squares are all 18 each. And so if I think about that, I'm going to have 66, and I have 3 times 18, which 54, and that means I have 12 left over. So this length of this, or the width of that rectangle down at the bottom there is 12 now. And then we repeat the process. So I'm going to look at 12, and I'm going to be like, okay, how many times is that going to 18? Because I have this rectangle that's 12 by 18 now. Okay, keeping in mind that these things are supposed to be squares, those 3 pieces over there. So I'm going to come over here, I'm going to do 18. Obviously 12 goes into that once, so 1 times 12, and we have 6 left over. So I'm going to come over here again, and I'm going to make my little 12 by 12 box right there. That's what this is in that corner. And then that means this is 6 right there. Okay? And then I'm going to do the same thing, except now we know that as unsquare-like as these things look, I'm going to have exactly 2 squares that fit in there. So that means that 12 equals 2 times 6 plus 0. And so what we've essentially done is we've taken this whole rectangle and we've broken it up into squares. But if you think about it, so I have 2 6 by 6 squares here, but 12 is a square, so I could actually tile 4 6 by 6s in there. And then with all these squares, I can tile this with a bunch of 6 by 6 squares, and then this one, and then this one, and so on. Because if you think about it, when I come back up and look at the numbers here, obviously 6 goes into 12, which means 6 goes into both of the numbers in the previous one, which means it also goes into 18. And then 12 goes into, and then 6 goes into 12 and 18, which means it must go into 66. And then it goes into 18 and 66, which means it must go into 150. So if we were looking for the greatest common divisor of 66 and 150, we've gone ahead and found this, because initially we said, oh, well, is 66 it? No, obviously not, because there's leftover. So then we find out, well, what happens? What's the greatest common divisor? Or does 18 go into 66? Nope, there's a remainder. Does 12 go into 18? Nope, there's a remainder. Does 6 go into 12? Yes. So that means 6 goes into all of the numbers that essentially make up 66 and 150. So at the end of it, we would say that the GCD of 66 and 150 is 6. And hopefully that kind of makes sense if you're thinking about it, because 6 times 11 would be 66. 6 times 25 is 150. So 11 and 25 clearly are relatively prime. So they're not going to have any other factors between them. So this makes sense. Okay. So this is essentially what we're going to be looking at for the Euclidean algorithm, at least to start off with. I'll be posting some more videos. I'm going to have a few more videos this time around to try and help people out. But as always, please feel free to send me a message through Twist. Send me a Zoom request and we can chat about it, or just send me an email, whatever works. Thank you.